Assalamu alaikum, my name is Ammonia HYSYS. You're watching my YouTube channel. Welcome back to an exciting series of lectures in which we are going to simulate the green ammonia. Till the last video, we have simulated the ammonia in our Aspen HYSYS. So now in this video, we will perform the heat integration, or you can say we will design a heat exchanger networks. So we need this recycle stream or original temperature is present on that stream. So except for this recycle 2, I will delete all this my equipment. So again, I will go to the brake connection, and here I can press this brake connection. So now this recycle stream is present as such. When we will perform all the heat exchanger, we will design all the heat exchanger networks. I will reconnect that stream, or you can say I will replace that stream at the end with this stream. So I am going to delete all my this equipment. So now you can see that I have deleted all my unwanted things, and now we are going to design a heat exchanger network via heat integration. So now the first thing that is present at the downstream of a ammonia conversion reactor is waste heat boiler. So for the waste heat boiler, I will press this heat exchanger over here. I will double click on it, and I will name it as waste heat boiler. And that's good to go. For the tube inlet, I can write as R effluent. For the tube outlet, I can write as out one. For the shell side, on the shell side, there will be water that will be converted to steam. And for the water, we will first of all we will place a separator over here, and this separator will act as a steam drum. And in this steam drum, we will be having our liquid stream. You can write here as water in, and its vapor will be going to our superheater. So it is you can write here as to superheatix, and its liquid will be going to our two waste heat boiler. So it will be going to our waste heat boiler. So now it is not solved because we hadn't specified our water inlet. We haven't specified a water in. So the pressure I will specify over here will specify the in the pressure of the steam that we want to make. So I am using here as 120 bar for my pressure. The molar flow or a ton flow rate you can use as 1000 tons per day of steam. So double click on it, and double click on it, and here you can see that we hadn't added our water till now in our fluid package. So I will again go to my we will again go to our properties, and in properties go to the component list, and in the component one list I will add my water. So that's good. Again, I will go to my simulation, press this. Yeah, so now you can see that we have returned back to our simulation environment, and I will double click on this water and double click on this, and here I can press this water as one. So I will press this OK, and temperature I'm not going to specify because we are not using economizer over here till now. When if I will use economizer, then I will add the sensible heat over here. But for in this scope or till now, I only want to add the latent heat in the waste heat boiler. So I will press this 0 over here, and you can see that maybe this stream has been solved. So now here this water uh, will be the shell side inlet of our waste heat boiler. So I can write here as 2 waste heat boiler, and here you can write as 2 waste heat boiler out. waste heat boiler out. So that is good. So now you can see that it says that unknown delta P. So go to the parameters, and here for the shell side and for the tube side, just give 0 delta pressure. So now it says that it is underspecified. So here I can give as vapor pressure 1. So now you can see that so this 1 means that my all latent heat here has been added, and it is good to go. So now this waste heat boiler out, I will recycle back to my steam drum. So I will again go to my flow sheet here. I will use the recycle, place it over here to waste heat boiler out. So this is to waste heat boiler out, and you can write as to waste heat boiler out recycle. So that is good. So it says that it is not solved. So now it is just taking a little bit of time. So you can drag it to here, place it over here, or you can just do that. So that is good. So now I will double click on it, and the design you will write as you will give this waste heat boiler inlet as well. So you can see that after connecting my recycle stream to waste heat boiler, so my this waste heat boiler has been unconverted. So I will double click on it and see that what error it is having. So flash failure in internal calculation. So it means that the pressure that we are using for water inlet is high. So I can decrease the pressure of from 120 bar to 100 bar. So yeah, it is a just a initial guess, initial hit and trial. So I can write as 100 bar. So I will press this stream drum also, and here it has already changed to 100 and 100 bar. So for this, I will press this, and here it is also good to go. So whenever you change the pressure, just double click, always double click on the steam drum and see that your all pressures have been changed. So in my case, it was changed, but in many cases, this recycling pressure, this pressure doesn't change, so you have to manually change it. So if I make it, drag it to here, so that is looking a little bit good. So I can rotate it. So that is good. So I have made a little bit of cosmetic changes, so that is good to go. So now the after our waste heat boiler, the second thing that is used is a superheater. So we will use another heat exchanger that will superheat the steam that we have generated. So again, I will go to my model sheet, and from the model sheet, I will place a heat exchanger over here, and I will double click on it. I will name it as super heater heat X. So that is good. So my tube inlet will be out 1 and tube out will be out 2. So or and then in the shell side, my inlet will be to superheater. So if I drag it a little bit down, so this will be my inlet to superheater, and here it will be to super heat x1. So that will be my outlet stream. So again, I will go to my parameters. I will give my shell and tube set pressure drop as 0. So again, after this, I will go to the worksheet, and here I have to specify one of the temperatures. So the temperature I will specify after these 310 degrees at 100 at 100 kgs. And so this is the last point. At after this point, the steam is being converted into superheated steam. So if I give 320 degree, so you can see that that was my initial guess. So I can increase this temperature to 350 degree. So after increasing my temperature 350 degree, so now you can see that here the temperature that you are getting is 358. So now the temperature difference between these two is very less. It is around 8.9 degrees. So you can reduce this to 345 degrees. And now you can see that 15-degree delta T is present. So that is good. So now you have superheated your steam and you have increased your superheated steam's temperature to, if I double click on it, to 345 degrees. So at the steam that you have generated from this reactor effluent is at 100 kilopascal, at 100, sorry, 100 bar and 345 degrees. To run a steam turbine, and from this steam turbine we will give power to our these compressors. So we will see that how we will be doing this as well in this simulation. So now we will use another heat exchanger, and this heat exchanger will be used to add the sensible heat for this water stream. So again, I will go to the my model palette. Here I will specify my heat exchanger, and here you can give inlet as out 2, and you can give out its outlet as out 3. So after this, at the shell site, you can write as W in, and you can write here as W out. So again, go to the parameters and give the pressure drop as 0 for both tube and shell site, and then you will go to the worksheet. And here I will specify the water inlet conditions. So these water inlet conditions are, you can say that this W in stream is present before the water inlet stream that is present at the inlet of our stream term. So if we want to increase the temperature, because in the waste heat boiler only latent heat is being added, so the waste heat boiler is generally acting as a evaporator. So before evaporator, you have to add economizers over here. So this heat exchanger is generally working as an economizer over here. So if I suppose that my water is present with me at 120 degrees, so it is just a suppose a temperature and pressure at 100 bar, that was our pressure. So and the molar flow rate of water is 100 tons, 100 tons per hour. Oh, sorry, it is 1000 tons per day. Sorry, 1000 tons per day. I will double click on it and press this one. So if I drag it a little bit above, you can see that it is not converging because this temperature is low and this temperature is high. So I can increase the temperature. So if I give as 150 degrees, so it is improving. So if I give as 200 degrees, so now you can say it is converged. But so the water in this water in is will have to be at 200 degrees, and this E104 is acting as a economizer. So we will see that how we can in our this flow sheet, how we can either we have to use a utility to increase the temperature of water to 200 degree, or we can utilize the heat from somewhere else in our model to 200 degree from ambient temperature. And one thing you can see that it is very near, so I can more increase the temperature to 220 degrees. And now you can see that 6 degrees delta T is present, so that is good. Approximately 10 to 15 degrees delta T is generally recommended over here. So now I can replace this water out by this stream. So before doing this, it is good that I again place a recycle stream over here. So I have placed a recycle. So you can place a recycle over here. So I will just place it over here. You can just place it over here. So here I will double click on it, and here you can its inlet is workout, and its outlet you can give as this water in. So you can give as water in. Where is water? So this is water in. So you can see that it is similar. It is converged. Till now, starting from 483 degrees, we have decreased the temperature to 316 degrees over till now over here. So after this, starting from 483, we have decreased the temperature to 316 degrees. So now the next heat exchanger will be our recycling gas or our recycle gas heater to increase the temperature from 4 degrees to 225 degrees. That was the inlet temperature of the reactor. So again, I will go to my model sheet, and here I will press this heat exchanger and I will place this over here. I will double click on it. I will select here as out 3, and here I can write as out 4. For my inlet stream, uh, here I can copy this recycle, and then after my original stream will be generated at the downstream of my separation drum, when the temperature will be reached to 400 degree, then I will replace these streams over here. So I can copy my this recycle. Where is this my recycle stream? So this is my recycle stream. I can second click on it. So here, where is copy? This is copy. So I will come to over here, and here I will paste it. So now I have copied my recycle stream over here. So if I double click on it, so you can see that here its temperature is 225 degree, but its temperature at the downstream of a separating drum, and that we have simulated in our previous video, was 4 degree for the separation of ammonia by the unconverted hydrogen and nitrogen. So here I can give its temperature as 4 degree, and after giving its temperature as 4 degree, I will double click on it, and I can write here this. So this is my recycle stream. I will give it over here, and you can write as recycle to reactor, and that is good. So again, I will make it a little bit shorter, and here we will go to the parameters, and here I will specify temperature as 0, and again here I can write as 0, and in the flow sheet, so now we want this temperature to be increased to 225 degrees. So we will see that either this stream out 3 has enough that it can increase its temperature to 225 degrees. So if I double click on it, so it says that this stream is not having enough, you can say enough energy to increase its temperature. So here I can give a smaller value. So you can give any smaller value, or you can see say that 200 degrees. So still this stream is temperature is lower than this, so I can more decrease the temperature to 150 degrees. So now you can see that my simulation has been solved. So now here, if I increase the temperature to 175 degrees, so now we are having a delta T of 10, that is good. So now you can see that our this out gases that were coming out of reactor is not having enough energy to increase the temperature back to 175 degrees. So what we will do that what we will do, we will increase the temperature here by our this heater that I had So we will see that what we will be doing here. So just again, I will place a recycle block over here. So I will go to my model, and this is my model recycle. So I will, so this is recycle to R, and its inlet is. So now you can see that again my conversion has been, my reactor has been converged. But why these all things have unconverged? Because the pressure, the inlet pressure is reduced to 189 degrees. So I will go to this heater block, and here I will increase the temperature to 250 degrees and see that my temperature hover, but what is my temperature at the inlet of the reactor. So it has increased to 196. I can increase temperature more if I give here as 300 degrees my inlet temperature. So now you can see that temperature has been increased to 211 degrees. So if I increase the temperature to 305 degrees, so you can see it is 212. Again, I can increase to 315 if I increase to 315. So you can see now it is equal to 225 degrees. That was my reactor inlet temperature. So that is good. So if I make it to over here, so that is good. You can see that now the temperature has been decreased to 187. So the next heat exchanger will be our cooling water heat exchanger, and I will again go to my model palette, and here I will you can select a heat exchanger over here. So I'm not going to simulate a heat exchanger. I will just place a cooler over here. I will place a cooler, so its inlet will be out 4, its outlet will be out 5. Energy will be, you can give us cooling water heat exchanger. Go to the sheet, increase the temperature up to you can say 40 degrees. Go to this properties, oh sorry, design and parameters, and uh, give the delta P as 0. So now you can see that the temperature has been decreased to 40 degrees, but we have to decrease the temperature up till you can say 4 or 3 degrees for the separation of ammonia. So now again, and these now so now the next two heat exchangers that we'll be using are the part of our refrigeration loop. So here I will double click on it, and you can write as out 5, and you can write as out 6. Go to this parameters and specify the pressure drop as 0 for both of them. Go to the worksheet, and after the first you can decrease or give the pressure up till 14 degrees, say. So it is, you have decreased the temperature to 14 degrees in the first heat exchanger. This heat exchanger is a part of your you can say your refrigeration cycle. So when in the next video we will simulate our refrigeration cycle in ammonia in this simulation. So we will converge these two heat exchangers as well. But in this video we are not going to converge these two heat exchangers. So this is out 6, and our last will be out 7. And go to the parameters, we will give the pressure drop as 0. Again, here we will give the pressure drop as 0. We will go to the worksheet, and here you can decrease the temperature to 3 degrees. So now we have decreased the temperature to 3 degrees, and now we are good to go and apply a separator over here. And this separator, I will press this separator, and this will be our ammonia separator. So that was the ammonia separator that I have deleted at the start of the video. So this is out 7. Top will be our recycling gases, and at the bottom will be our ammonia. So you can write as liquid ammonia. So now you can see that this simulation on this steam drum has also been solved. And if I press this liquid ammonia again, so you can see that 1007 tons of ammonia is being produced in this simulation. And out of 1007.9824% ammonia is present, and a small amount of nitrogen and hydrogen is also accompanying. So if you multiply 0.9824 with 1007, so it is nearly equal to 990 to 995 tons of ammonia. So that is good to go for me. So this is the liquid ammonia we have generated. So again I will, so we have to connect this recycling gases with our this stream. So again I can I first give me the so I have to connect this recycling stream with this stream. So that is the last thing in the scope of this video. So I will place a recycle over here, double click on it. So its inlet is recycling, and its outlet will be recycle to 3. So now you can see that my this recycle stream is also converged. So what we have done that from the separator, the unreacted, or you can say unconverted nitrogen and hydrogen that was at 3 degrees, the temperature was reduced to 3 degrees because we wanted to separate out ammonia. So this 3 degree unreacted nitrogen and hydrogen is heated by a heat exchanger that was present at the downstream of our ammonia conversion reactor. And this, after increasing their temperature, we have sent these gases back to the reactor after increasing their temperature to 223 or 225 degrees for the conversion reaction. So, so now one thing is remaining in this video, that we have to simulate a steam turbine, and these two heat exchangers are the part of a refrigeration cycle, and we will converge in our next video. So the last thing is for this video is to simulate a steam turbine and use the power of this steam turbine to run our compressors. So here I will go to the, sorry, not go to the properties. I will again go to my modify sheet here, model streams, model palette. Here I will select a expander over here. So here this is the expander, and from the expander its inlet is, if I drag it, inlet is to superheater X, and outlet is turbine out, turbine out. Energy you can write as turbine E. So that's good. In the worksheet, just give a condensing pressure over here. So I can give as 10 kilopascal my condensing pressure. So now this turbine is generating power 9,143 kilowatt, but if I see my compressors stages, so these powers are greater than So 5,000, 5,000, and here it is 5,000. So approximately the four stages are taking 20. You can say that 20,000 kilowatt of power. So if I make it as 0.1, or here if I can write as 1. So now you can see that my power has been increased. So now you can see that power is increased to 11,000 kilowatts. So now you can see that my power has been increased to 11,000. So this compressor stage energy requirement is 5,100, and this compressor is also having 5,180. So so we can use this energy produced by this steam turbine to run the shaft of these two compressors. In Aspen HYSYS, how we will simulate it? So again, go to this. We cannot use this energy to run all the four compressor shaft, because their energy is because the energy requirement for the all stages is 20,000. What we are generating with this turbine is only you can say 11,000. For the 9,000 deficit, you can use a motor. If not a motor, you can use a steam generator to produce steam, and then you can use that steam for running these two turbines of these two shafts of the compressors. So we can do this with the help of our balance. So go to this balance block that is present in Aspen HYSYS. So this is balance. Double click on it. So the inlet stream will be my turbine energy. So where is turbine? So I can write as turbine energy. For the outlet, I can write as since the second and the third stages of the compressor, I can connect it over here. So sin where is C? So this is my first energy, and my second is, I drag it a little bit down. So my second one is this one. So sin C2E sin. So that is. So now you can see that the heat flow of that stream was 11,000, and the heat flow or the power requirement for these two compressors is around 10,200 200 kilowatts. So the excess thing will be considered as losses. For losses, we have to specify another stream, that is heat stream, and we will specify as a losses. Just rename this stream to losses stream. So now you can see that I have renamed this stream to losses energy stream, and here I can select this losses stream. So this is losses. So now it says that we unknown balance type. Go to these parameters and select flow, and then you can see that my this balance has been solved. So now what we have done, we have just used the energy or the heat flow or the power generated by our this steam turbine to run the two shafts of our second and third stage compressor. The remaining power that was uh, here, you can see that here the it is 5,000, and the first stage compressor also uses 5,000 kilowatt of power. So for this you have to apply a new steam turbine, or you can also use motors over here for their generation, but you cannot generate this power from this effluent stream of the reactor. So that's all for this video. Inshallah, meet you in the next video. Assalamu alaikum.